So, explaining this question is our intermediate goal. So we are going to start from the statistical independence assumption, right? Like suppose that A and B are independent binary random variables, then choose a wrong statement. So we learned independence in chapter 2, so we are going to borrow properties from there. What is not a property of independent random variables? The answer is, so the first answer is that probability of A does not change even if B already happened. This is independence. And B is, this is the special rule of multiplication, law of multiplication, right? So the intersection probability can be denoted as, like, expressed as the multiplication of two simple probabilities. Third, probability of A does not depend on whether B happened or not. Either B happened or not, probability of A does not change. And D, this is the special law of addition rule. Does not make sense in here. Remember, this is true when A and B are mutually exclusive. Has nothing to do with statistical independence. And finally, like B did not happen, but still that does not change the probability of A. So the answer is D. A, B, C, E are just properties of independent, statistical independence. Especially, we are going to use part, like the answer B, the special multiplication rule. Multiplication rule is what we are going to use. That's why we made independence assumption. So we have this, but you can generalize this idea to this, right? When you have three independent variables, still you can just multiply all the simple probabilities to obtain the intersections, right? So the left-hand side is the probability that A happened, and B happened, and C happened at the same time. All three happen at the same time. That probability can be written as probability of A times probability of B times probability of C. You may include more events as long as they are independent, right? If everything is independent, you can expand this equality, like including more intersections and more multiplications, right? So this is our tool to simplify the algebra. Okay, then the first example is when there are only two reservations, say, right? So there are only two reservations are made, and the cancellation probability is the same, 10%. So there are only two tickets sold, and one of them or both can be canceled. They are independent. And think about this probability. What is the probability that A's reservation is canceled, but B's not? Pretty simple, okay? So just guess it. It is pretty simple question. I think many of you have chosen D, 10%, because A is canceled but B is not, but only A is canceled, so apply 10%, right? Cancel happened once. That is wrong. That is wrong. The answer is 9%, because even though I gave you probability of cancellation, still you have to count the reservation that is not canceled. The probability of non-cancellation is 90%. So this is another event, right? So this definitely, cancellation is something that happened, but also even if it is not canceled, that is another event that actually happened with 90%. So we can write it this way. The probability I asked is the probability that A is canceled. 1 stands for cancellation, but B was not canceled. 0 stands for not canceled. So they happen at the same time, which is implied by the intersection. And independence assumption implies that you can just split them into each probability. So probability of cancellation and probability of non-cancellation. And you know what they are. 0.1, 10%, 90%. So the answer is 9%, right? So this is the answer. Like 9% is the answer. So I think many of you would have chosen 10%, but it's pretty simple to understand why it is not 10%. So first catch is that even if I say one reservation is canceled, still you have to imagine what did not happen. That is also something happened, even if it did not happen, right? You have to take those probabilities into account. My second question, we are going to expand our question to make it more tricky and complicated. Same thing, we have two reservations and everything is the same, but now I'm asking you what is the probability that there is one cancellation, only one cancellation out of two. Think about that, just guess it. So it's like IQ test. Now, if you understood the previous question, now you may choose 9%. But there is another trap. The answer is not 99%. So it is different from the previous question. Let me explain. The better way to explain this is making up like a table for all possible outcomes. So there are only 4 possible outcomes because there are 2 tickets, cancel or not for each ticket. So you can think about 4 cases, and in the top left one, there are 2 cancellations. A is canceled, B is canceled. And here, A was not canceled, but B is. And here, A is canceled, but B is not. And in here, both are not canceled. So when I say only one ticket was canceled, it includes these 2 outcomes, right? That's the difference. In the previous question, it was only about this event, this outcome, right? This is 9%. I explained why this is 9%. A is canceled, but B is not. That is 9%. But now in this question, you have to think about this. When I say only one is canceled, it may be A is canceled, or it may be B is canceled. So additional outcome should be taken into account now. So the solution goes like this. The probability that only one ticket is canceled equals this outcome or that outcome. So this is simple way to calculate probability that we learned in chapter 1. Pretty simple, right? Out of 4 outcomes, we are interested in two of them. And each probability, you know how to calculate that using the independence assumption, like multiplication rule. So it is 9%. By the same logic, it is 9%. So in the end, you get 2 9%. So 18% is the correct answer. The answer is 18%. Okay, so like earlier, the first question I told you, one typical common mistake is not counting the outcome that is not canceled, not counting non-cancellation. Even though it happens with 90%, still you may forget that part. And second common mistake is when I say only one ticket is canceled, it actually may include many different possible scenarios. Cancellation by A, cancellation by B, right? So you have to imagine all the possible scenarios, all the possible combination of cancellations or non-cancellations, right? So that's the tricky part, okay, right? You know how it works, okay? So we are expanding our idea step by step. Still a lot more to go. I hope you get what I'm saying up to here, because it's pretty simple example with 2 reservations. Now, we are expanding the case to 3 reservations, right? Everything is the same, but now there was another reservation coming in, like C, passenger C now bought a ticket, and probability of cancellation is the same, and it is also independent of the other reservations. When there are 3 reservations and cancellation probability is 10, what is the probability that the number of cancellation is 1? Only one of them is canceled. There is no trap. If you follow the same ideas what I have done in the previous 2 questions, you should be able to calculate that. Just apply the same logic to more complicated case. The algebra will be a little more tricky. Okay, so if you want to try this by yourself, try it now. I am going to I'll continue. So the idea is, first, like in general, the safest way to handle this question is to count all the possible cases, right? So there are 3 reservations, and each of them can be canceled or not. So there are 2 by 2 by 2 cases. There are 8 possible outcomes, okay? And calculate their probabilities and count how many, like what is the probability of only one reservation being canceled. Like this is that, right? There are 8 possible combinations. So the first outcome is none is canceled. The second one, only A is canceled, only B is canceled, only C is canceled. And here, A and B are canceled, and A and C are canceled, B and C are canceled, and everything is canceled. So this is all possibilities. And we are interested in these 3 outcomes, right? So the first outcome has 0 cancellation, and the last outcome has 3 cancellations, and the second last ones are 2 cancellations. So we are interested only in these 3 outcomes. So I am going to calculate probability for each of these outcomes and add them. That is exactly how we obtain this guy. Okay, let's think about that. So as I said, the probability that there is only one cancellation equals A is canceled but the other is not. B is canceled but the other is not. C is canceled but the other is not. These 3 possible scenarios. You have to include all of these. And then how to calculate the first one? How to calculate the first probability? Use independence, multiplication rule. Probability of A canceled times probability B not canceled, probability C not canceled, like this. So cancellation probability times non-cancellation probabilities from B and C. Similarly, B is canceled, but A and C not. So 0.9 multiplied twice. Cancellation 0.1, non-cancellation 0.9. So you can calculate probability of intersection using multiplication rule, using the independence assumption. In the end, actually the 3 different scenarios have the same probability, right? Because it's the same thing, like just 0.1 times 0.9 times 0.9. So in the end, you get 3 times same probability, right? This is how we calculate the probability from the very beginning, counting all the possible cases. We are going to extract formula from this idea. Okay, so let's compare the answers. When you had 2 reservations and when you calculate probability of only 1 cancellation, you get this. Probability of cancel, probability of non-cancellation, and there are 2 possible scenarios. Okay, when there are 3 reservations, the probability of 1 cancellation is like there are 3 different scenarios, but still 1 is canceled and the other 2 are not. Okay, so like first principle we can extract, we can learn from this algebra is this. First, you have to think about the number of possible outcomes in that event, right? The event we are interested in is one cancellation happened. And how many outcomes are included in that event depends on just combinations, how you like making different combinations of ones and zeros. And the second part is the probability of single outcome, each outcome, right? As you can see, it is pretty simple, right? Because it's about multiplication of success probability and failure probability, right? So this part is rather simple. We are going to discuss more about this, how to calculate the probability of a single outcome. And simple, right? You know, independence assumption implies the multiplication rule, so basically you just multiply. The rule is you are going to multiply 0.1 as many times as cancellations. Because I assume there is only one cancellation, that's why 0.1 is multiplied once. If you are interested in like two cancellations, then you'd have to multiply 0.1 twice, right? So there will be 2 success. Similarly, 0.9 is multiplied as many times as non-cancellations, right? Like this and like this. So remember, the principle is pretty simple. Multiply the probability corresponding to each outcome. So if there are certain number of success, you have to multiply that many number of probability of success. If there are certain number of failure, you have to multiply as many probability of failure, right? So that part does not depend on who canceled or who didn't. It is purely multiplication and the same number multiplication, right? So that's because we assume that the probability is the same for every ticket, right? The probability of success, probability of failure does not change across experiment. So we can extract this pattern from this observation. Pretty simple. In general setup, we assume that there are n trials and experiment is repeated n times, and in our example, that is the number of reservations, right? One reservation is one experiment because one reservation can end up either canceled or not, right? So P is the probability of success, which is 10% in our example, right? And we suppose that we are interested in the number of successes, capital Y, equals to a specific number, like 1 in our example, but in general, I will denote it as lowercase y. And then so actually we have 3 numbers, 2 parameters, and 1 lowercase y that we are just interested in, the number that we are interested in. And then you can write the latter part, generalize these guys to this. So P is the success probability. That happens why? Because we assume we are interested in the number of success equals y. So that's multiplied P times. And then, as I said, don't forget the failures. When you observe y number of successes, that means the other n minus y are failures. So you have to multiply failure probability as like that many times, right? N minus y is the number of failures you observe, so you have to multiply 1 minus p there. Okay, so this is the basic formula for the second part, right? So second part is pretty easy to handle using the independence assumption. Now I am going to think about 4 reservations case. Everything is the same, just there was another ticket order. So now let's change it, because cancellation of one cancellation is easy, just simple extension from the previous question. Now let's consider the probability of two cancellations, right? And as I said, this is the general setup, and this part is pretty straightforward. Even if like you get 4 or 5 reservations, like simple algebra as long as you have calculator. But now think about this part. That is our next task, which I'll leave it to you for now. I hope you enjoy this. Try it by yourself, right? And then I will explain that in the next video. Thank you for watching. See you later.